In this training module, we'll learn how to calibrate and tune the FD322 APU. First, the sensitivity needs to be calibrated using a quick and easy software procedure. Then it's time to tune the APU to detect intrusions and reject nuisance alarm sources. Tuning for detection is straightforward, but it may take several tuning iterations to get nuisance rejection just right. It takes some time to experience the range of weather conditions to which the fence line will be exposed, so the APU tuning may evolve a bit over time. Regardless of the methods used, there should be a defined test period for monitoring and fine-tuning the system before it's put online. The sensitivity calibration must be executed from the terminal mode. As mentioned earlier, the FD322 tuning software can accomplish this, or a terminal emulator program can be used. Either way, a two-step process is involved in calibration. First, the current time and date need to be set so that the APU can correctly tag event occurrences. Second, a measurement of system optical loss must be made in order to set the APU sensitivity. A short video segment will now be shown to illustrate this process. The first step is physically connecting the APU's RS-232 port to your laptop using a serial connection such as a direct serial port or a USB to RS-232 converter. Then, run the FD322 tuning software. Once that's done, the APU must be connected to the appropriate serial port in the software. Select the port from the drop-down list and hit the Connect button, and in a second or two the dialog box will indicate that the APU is connected. Next, access the terminal mode and the display shows that you're connected. To calibrate the device, enter the calibration mode by typing CALIB and enter. To set the time and date, type D and enter, and the currently stored time is displayed. Let's set the time by typing in 1740 and enter. The display shows that the revised time has been accepted. Then hit enter again and the currently stored date is displayed. Enter the new date in a similar fashion and you're done setting the time and date. The next step is measuring the loss and calibrating the unit for sensitivity. Access the Calibrate menu once again and type ML and enter to enter the calibration mode, and then confirm that you really want to calibrate. At that point, the display shows the last stored loss measurement. In this case, the loss was 0 dB and it was stored at 1:58 p.m. on October 3rd. Once you've entered the calibration mode, the next step is to vigorously shake the fence for about 10 seconds. Note that the loss display doesn't do anything while you're shaking the fence. It continues to display the last measured value. Once you're done shaking the fence, take a small tool such as a screwdriver and insert it into the test hole on the APU and depress the internal test button. As can be seen, the APU has saved the new loss value. In this case, it was 1 dB and it was stored on November 12th at 6:07 p.m. At this point, you're ready to tune the APU. This video has demonstrated in real time how long it takes to calibrate the unit. It's very easy and takes only a minute or two. Let's have a quick review of the APU's efficient and effective parameter set before diving into the tuning process. We'll be adjusting sensitivity, event count, and low-frequency cutoff for the climb and cut processors as our primary tools. We've also got the wind rejection algorithm at our disposal for nuisance alarm sources. So let's talk about how these adjustments work together to tune our fence sensor. You'll first need to connect the APU to your PC and run the tuning software. It's best to start out with default parameters, so use the parameter editor to verify this and reset the APU if necessary. We'll be working on climbs first, so run the real-time mode and observe the fence signal as the test intruder scales the fence. Adjust the climb sensitivity so that an alarm is caused when the intruder's waist level reaches the top of the fence. If more or less sensitivity is required, one of the ways to accomplish this is to lower the event count to catch the climber sooner, or raise the event count for a later catch. However, avoid low event counts, that is, 2 or less, since nuisance alarm sources such as a branch blowing in the wind or an animal brushing up against the fence may create unwanted alarms. Excessive sensitivity can equate to nuisance alarms, so interactively adjust sensitivity and event count for the best compromise. Now for a brief word about your test intruder. The FD322 has been designed to easily detect an ordinary, non-stealthy intruder, so be sure to choose an appropriate test climber of average build and height. Make sure he's dressed in the manner of a common intruder, including ordinary footwear, and make sure he performs his test climbs in a non-stealthy way. The FD322 is capable of detecting the stealthy Super Ninja guy if you crank up the sensitivity to the max. However, nuisance alarms will be an issue since the parameter set is limited. To properly catch the Super Ninja, you'll need one of our more advanced APUs. Now let's move on to cut intrusions. The first step is to set the cut event count to the desired value. It should be set less than or equal to the number of cuts required to create a security breach. It's a good idea to keep the count to 10 or less, however. Perform your cut simulations and adjust the cut sensitivity so that an alarm occurs when the set number of simulations has been made. Note that it's best for each simulated cut to create only one event. You may need to record and review some spectral data files using the tuning software's real-time and replay modes to help verify this. Once again, remember that excess sensitivity equals nuisance alarms. Rejection of nuisance alarm sources is next on the tuning agenda. There are two parameters that desensitize the APU to nuisance signals: low-frequency cutoff and wind rejection. Both climb and cut processors have independently adjustable frequency cutoffs. However, the wind rejection algorithm affects both processors equally. Both the wind rejection and frequency cutoff settings require analysis of spectral data files to optimize performance. Real-time mode signal recordings and internal alarm spectral history files can be analyzed in the replay mode to this end. The internally stored spectral data records can be especially useful considering that nuisance adjustments are done on an iterative basis over time. The wide range of weather-related nuisance alarms will be automatically recorded by the APU and can be recalled for analysis at any time. Many nuisance alarm sources, such as wind, power frequency vibrations, and train and vehicular traffic, have strong low-frequency components that can often be eliminated or reduced using the low-frequency cutoff parameter. On the other hand, climb and cut intrusions normally include components at all frequencies. Analysis of spectral data files for frequency content using the replay mode allows comparison of intrusion signals to nuisance signals. Adjustment of the low-frequency cutoff parameter can often dramatically improve nuisance alarm rejection. For example, wind signals typically consist of mostly low frequencies below about 200 Hz. Even though the wind rejection algorithms are very effective, it's still best to eliminate as much low-frequency noise as possible using the low-frequency cutoff parameter. If wind nuisance alarms still exist, raising the wind rejection parameter will be even more effective after the low-frequency noise has been eliminated. Adjust wind rejection processing over time until nuisance alarm rejection and intrusion detection goals are achieved. There are two remaining parameters, and they're in the miscellaneous section of the parameter table. They include a tamper switch control and an alarm relay time control. If your NEMA enclosure is equipped with a mechanical switch that operates when the enclosure is opened, the tamper switch enable/disable parameter allows monitoring of that event. When enabled, the alarm control system is notified by the APU when the enclosure is opened. The alarm relay time can be adjusted to allow the relay to remain in an alarm state for an interval between 1 and 10 seconds. The setting for this will depend on the requirements of the alarm monitoring system. There are a number of recommendations and sometimes site-specific requirements for your tuning activities. Of course, you'll need the tuning software and a laptop PC. And it helps to have the product manual available, even if it's only viewable on your laptop. Personal protection equipment is always a good idea, and many sites have specific requirements for you to even be allowed on site. This may include, but is not limited to, protective and/or electrically non-conductive footwear, safety glasses, and a hard hat. It's highly recommended that the test intruder have a good pair of gloves to protect his hands while climbing. You'll also need some tools and other items to simulate intrusions. When tuning for climb intrusions, It's important that the test climbers simulate climbing the same way that a potential intruder would climb. Remember that the FD322 works best when detecting ordinary, non-stealthy intruders. When climbing, if possible, bring your waist even with the top fence rail and then carefully jump back down. Make adjustments to the climb processor parameters so that climb intrusions cause an alarm by the time the climber's waist reaches the fence top. Note that the climber's weight, pace, technique, and foot apparel can greatly impact detection. Choose and equip your test climber appropriately to simulate an ordinary intruder. When tuning for cut intrusions, start out by using a large, flat-bladed screwdriver to tap the fence. Wait a second between each tap. The goal is to create an alarm when the fence is tapped the number of times equal to your event count. Be wary if multiple events are created with a single tap. This may indicate that your system is tuned too sensitive. Be sure to tap the fence in different areas since there will be a variance in susceptibility to vibrations. Reinforced sections or the area around the fence posts may be less sensitive than other parts of the zone. Remember to make changes to the cut processor parameters when performing your cut intrusion tuning. Finally, there are several other ways to simulate cut intrusions that may be appropriate for your site. Customers will generally frown upon your cutting their fence when tuning for intrusions. However, a good way to simulate an actual cut is to first tightly attach a stainless steel wire tie around one of the fence diamonds and then cut the tie with a good pair of wire cutters. This is more time-consuming than tapping with a screwdriver, but more accurately simulates a cut. And if you're worried about someone cutting the fence with a hacksaw, you can use a long, threaded screw or bolt that's dragged back and forth through the fence to simulate such an intrusion. This concludes our discussion of FD322 calibration and tuning.